I know it's a P. That's why it's pi. All right. Okay, so let's sort of work through in the last remaining bit. We're going to set up, we're going to sort of move through this problem and see what we can do with it. So there are different ways to think about this, to tackle it analytically. But we'll take Simon's model, Simon's approach to start with, and I'll point to what this will mean we'll miss the first mover completely. We'll be very happy, it all looks good, we get a nice distribution out, but it could be you literally miss the biggest elephant in the room. Okay, so, or figuratively, or one of those things, literally, figuratively, metaphorically. So we're going to have size of group I, right? So we've got a K. And then we have the number of groups that have this size K. So this could be the number of times a word appears. So the appears so many times, and appears so many times, chicken appears so many times. And then we want to know the number of groups that have that size, right? So there's a city sizes, the number of cities that have a size. So they're going to be right out there, they're going to be unique. There's the biggest city, lots of little ones, especially with books, of course. We have many words that appear once, less words that appear twice, and then we have the, which is right out there by itself. Right, so we want these two pieces. So how does this evolve over time? This is really going to be our, right, we're trying to get a probability distribution or a zip distribution. We want one of those things. We know that they're connected, they're swaps of each other. So how does this thing evolve with time? So we know a couple of things. So at any point in time, if we sum over k n sub k, right, so this is the number of groups that have size k, we multiply them by the number of elements. This is adding up all of the elements. That is all of the elements that are in groups of size k. We sum over k. We've got all of the elements total. And we know that that's just t, because this is a very simple thing. There's one element, two element, three elements as a function of time. Right? Time could speed up. We could do that. The adding could speed. That's the rate thing, but that's the way we're doing it. Okay, good. Okay, so that's useful. That's a normalization. And then we're going to set up this thing. So we want probability of choosing an elephant that belongs to a group of size k. As I said, we randomly choose an element, and then we replicate it, and that has this effect of making its group bigger. So how do we get this? So first of all, there are this many groups, right, just by definition, that have size k. So we need to count all of those up. And this is the same as what we had on the previous slide. So there are k so many k times n sub k elephants in those groups. So, right, and t elephants overall. So this is our little probability at each time step of choosing a elephant that's in a group of size k. Right. So we don't care, if they're we take all the groups that are of size 7. It doesn't matter what their colors are. We're not thinking about that. We're taking them. We want to know if this group's of size 7, or this one, or this one, all of them one of them gets replicated. Because now we know that one of those groups went to a group of size 8, and that's the accounting we need to make. So it means we lose a group of size 7 and we gain a group of size 8. So that's the little thing we have to account for. Does this seem okay? Right. So that's a fundamental thing. So this is how things will change, right? So as I said, we can have an elephant that belongs to a group of k. It gets replicated. So now it's part of a group of size k plus 1. So that means we lose it. If it's part of a group of size k minus 1, that means we're going to get we're going to add 1 to our number of groups of size k, right? So we lose, the number of groups of size k goes down by 1, and here it goes up by 1. So that's the simple thing. So the number of groups of k, size k, times t plus 1, what we had before, we lose 1. And this happens with this probability. So there are a couple pieces here. 1 minus rho was the thing we introduced at the start. If with probability rho we make a new one. This is not happening. With probability 1 minus rho we do the replication. So that has to be the case. And then this is the probability of choosing a group of size k. Right, so two steps. Right? There's that preliminary part of the algorithm, which is right. Okay. So here we get one more group of size k because we came from a group of k minus 1, got a little bit bigger, so that changes positively. And it's a similar looking thing. We had to be replicating 1 minus rho. And then we have to be careful here. We're choosing from a group of size k minus 1. So if we just look at our little probability, it's k minus 1 times, and it's nk minus 1 here on the, this piece. Right? So we just replace k with k minus 1. So this is a reasonable setup. So we can kind of start putting these things together. These are exactly what happens in both of those cases. And we're going to make some sneaky approximations. For the number of groups of size 1, right? So these are the unique groups. They have a special behavior. So the new elephant is a new flavor altogether. And that is a +1, right? So there's groups of size 1. There's one more of them. And that just happens with probability rho. Just happens with probability rho. Or it could be a unique elephant is replicated. So we lose one of our groups of size 1. And that's more like what we had before. This is probably 1 minus rho that we're doing replication. And then we had to have chosen an elephant that is in a group of size 1. And so that's the number of groups of size 1. There's really a 1 here. Right? It's 1 times this. Usually we had k times nk. So it's 1 times this divided by t. So we just a little bit of accounting at the low end. So we can write a general we can write a general expression for what's happening to n of k, but we just have this kind of boundary condition here, an injection thing. Okay. So this is going to be the setup. This is what we expect. This is an average, right? This is what we expect to happen for the number of groups of size k as we go from t to t plus 1. So this is the change in it. This is the difference, right? Number of groups of size k at time t plus 1 minus the number of groups of size k at t. This is what we expect on average to get. We have to have replicated. That's a 1 minus rho thing. And then we get 1 with this probability, and then minus 1 with this probability. So this is what we expect to happen. Right? These are the two pieces we had on the slide before. This is the top piece we had. We lose 1 because it went from a k to a k plus 1 group. And we get 1 more if we had a group in a k minus, an elephant in a group of size k minus 1 replicating. So now it's in a group of size k. Right? So group of size 12. We're talking about 12. So a group of size 11 moved to a 12, or a 12 moved to a 13. We lose 1 in that case. We get 1 in this case. So this is all true. The lies begin soon. And for k equals 1, we have a slightly different thing. It all looks the same. This is really the same on the right-hand side, but we just have this +1 rho instead of all of this contraption here. It's just the expected change here is we get 1 more if there's an innovation, right? There's a new node a new type we've never seen before, and we lose 1 if one of our unique groups replicates, right? So an elephant that had no friends gets a friend, then we lose that there. We lose 1 from our total count of groups that only appear once. The hapax legomena, right? The words that appear once in a text. Right? This is the setup. Okay. Good, good. And then what are we going to do with this? All right. So we're going to assume a couple of pieces here. So one is, if this works out, and we can check this later on, right, that we'd like this to happen, that as this thing grows, we're starting to get a distribution that's stabilizing in the sense that it's just some form multiplied by t. May not work out, but we're going to try that. Drop expectations, and so now we have this weird thing where the elephants can be fractional and so on, but it's okay over large time scales. We're going to say on average this is happening. This is for later. Let me put this here. This is the number of groups that have size k. Yeah, that's fair. Right? This is simply a number of groups of size k. Rho times t is the number of different groups. That's the number of, because it's the number of actually unique elements. And if we put this piece in here, this little nkt, right, we're assuming that. So this is now the thing that's varying. This is just a straight t, multiplying it. Those cancel, and we get a simple thing here. All right, don't have to worry about that yet. All right, so we had all of this on top, And that's just, we're just going to drop it down to two pieces here. We're going to say, just drop the expectations. We're going to say it's just growing incrementally by this fraction. And hopefully the equations will sort of carry this error we've made and kind of, it'll be okay. Simple thing happens on this left-hand side. This is a t plus 1 here and a t. So, and they're just multiplying, right? This isn't a function. This is just a number times t plus 1. And this is just that number again times t. So these pieces cancel, right? They're gone. So it's just nk on the left. And then we've replaced these, the number of groups of size k minus 1 and size k as just the simple number times t. Again, simple times number times t, so they cancel. This may be hard to see at this point, but if we didn't have this simple linear thing, if we had groups being selected by some power that was not linear, this is much more complicated, right? You can't do all this magic. Things don't clean up quite as well. But what you can see at this point is like this was an okay assumption to make that the number of groups is scaling or just growing linearly as t, because this is cleaned up, right? There's no t sitting in here anymore. This is just an n sub k here. Things have cleaned up pretty well. We've got our 1 minus rho here. Some k's are sitting around. And now you can see we have a thing that we could unwrap and get n sub k as a function of n sub k minus 1, which is a difference equation. And then we could say, okay, we know what m1 is, and then we know what n2 is, and what n3 is, and n4 is, right? We could build out a whole thing and then check against actual reality. So if you rearrange this, right? Well, this is clean. This is not quite rearranged. This is cleaning this bit up. So we've just got n sub k here. I think the t's have been taken away. So we want to put the, yeah, right. So we're going to bring all of this over here with a 1 minus rho attached to it. Let me see if I can help you understand that, right? So this is going to be, there's a 1 minus rho times this blob. It's a minus sign. So when we bring it over here, we get plus 1 minus rho, and there was a k. K. And all of this is multiplying n sub k. N sub k was here with a 1. So we've got n sub k times this blob, and then we've got this blob times n sub k minus 1. So this is looking pretty good, because now we can just say n sub k is blob divided by blob times n sub k minus 1. So we have a little thing that we can just feed in an n sub 1, and we could get n2, n3, n4, n5. Right, we could stop there, right? That would be fine. So that's the growth thing. But we want to know if we get an actual formula out of this thing. Could we do that? We want to know what it's like for large k. Yeah? We'd like to see that. It's not obvious from this that this will produce, I don't think it should be obvious. Maybe it might be at some point too, but that it would produce a power law, right? So this is the number of groups of size k. So we're going to start with the number of groups of size 1, 2, 3, 4. So this is getting out the size frequency distribution. It's not getting out Zipf's law explicitly. Right? There are different approaches. Right? It's not getting, but when we plot whatever we get out of here, we're going to have m1, n2, n3, n4, n5. So that's going to decrease, like, it's going to decrease as a power law. It's the size frequency distribution. So we're looking for gamma as the exponent, minus gamma as the exponent. You can solve it exactly. Yes. You can also mess around with it and just kind of expand and do naughty Taylor things and just fiddle around with it. That's also a possibility. I could just delete that. Okay, so this is what you get out. Pretty spectacular. Is that it is k to the minus gamma, right? It does produce a power law. And then there's this beautiful thing here, right? So this is an exponent. It's gamma. I've tried to keep that consistent throughout, right? So minus gamma is the setup for size frequency distributions. And the problem is there's a row for a rate here. Zipf's law is alpha, right? I had alpha for Zipf's law, yes. Should be consistent. It's coded in the LaTeX, right? Never put alpha, you always give it a funny name. Okay, so gamma equals this blob. That's a nice looking thing, 2 minus rho of 1 minus rho. It's actually a little bit better to say this is really 1 minus rho plus 1 on top, and then some things cancel, we can get a 1 plus this. So that's going to look pretty clean. And we can think about how that behaves as a function of rho.